So, I really liked jumping into these notes. This was a lot of fun for me because I don't know anything about intuitionist type theory. I've tried to read up on it a couple times and I couldn't quite really make sense of it. Or I was starting to make sense of it and starting to get something down, but I didn't really get it. And one thing that I have found is that I always understand things better when I actually read something written by somebody who is trying to say, like, trying to introduce the idea, right? Because they don't get to cut corners, they don't get to skip anything, and I appreciate that about this. So I enjoy that a lot. But I also know that as I started reading it, like, this is clearly written by somebody with who's assuming a fair amount of familiarity with logic, from the background of logic. And my suspicion is that there isn't a ton of that for a lot of us in this room. I know when James told me about it, he was like, I always have to think a lot harder than I feel like I should on page 2. And so I'm sort of using that as my jumping off point here. I'm going to talk about what's going on in these notes, and then I'm going to take a really big digression through sort of what you would standardly run into in sort of an introductory logic, well, not an introductory logic course, but in a standard, precise treatment and presentation of sort of very, very, very basic logic. I'm just going to focus on Boolean logic because it'll be easier. But I'm going to do that because I think it'll help sort of clarify what's going on when he's talking about things like propositions and judgments and all of this stuff. And also because I think it's useful to keep in mind what I'm going to be talking about, even though he's then going to completely intentionally obliterate the distinctions that I'm going to be drawing. I think it's a helpful sort of thing to have in the background. Okay, so let's go ahead and jump right in. What are propositions, right? Well, propositions, how legible is that? That's good enough. Okay, so propositions, what are propositions supposed to be? Well, they're supposed to play multiple roles. Sort of just theoretically, the thing that they're supposed to do, they're supposed to play multiple roles. So they're supposed to be meanings of sentences. They're supposed to be bearers of truth and falsity. And they're supposed to be the objects of attitudes, like belief or fear, knowledge, and a bunch of other things. And judgment, I think, can also be sort of fit into this last category here. They're the things we judge, where we make judgment about. So they're also objects of judgments, we'll say. And the reason I wanted to start here is because the notion of a proposition, one of the main reasons that people will talk about it is because we want to be able to say that, we want to be able to say things like this. Snow is white, the sentence, snow is white, and the French sentence, la neige est blanche, mean the same thing. And the idea is, or one of the ideas is, that phrase, the same thing, let's take that really literally. There is a thing that they mean, and it is the same thing, right? So the sentence, snow is white, and the sentence, la neige est blanche, have a meaning, and their meaning is the same, one and the same thing. So there is this numerically identical thing that is the proposition, snow is white, that is expressed in different languages by different strings of letters. So that's sort of the meanings of sentences thing. And then the idea is, well, they can also play this role of being true or false, right? So if I want to say the sentence "snow is white" is true, the thought is I can actually just say it's true because it expresses a proposition that's true. So the proposition is the thing that's sort of fundamentally true or false, and then everything else is true or false derivatively from that. And then, so that's the bearers of truth thing. And then finally, what am I talking about as objects of attitudes? Well, if I say I believe that snow is white, that doesn't have to involve a sentence of English, right? I'm using English to express my belief, but the belief, the thought is directed towards this proposition, whatever it is, right? So if I say, if I'm afraid that there's a bear outside the door, I'm related to the same thing that you would be related to if you hope that there's a bear outside the door. Whatever it is, I'm not saying what propositions are, but there's a thing out there that is whatever the heck it is, the proposition that there's a bear outside the door, and it's what you are related to with your hope, and I'm related to with my fear. and so on. So that's sort of these three different things that propositions, these three fundamentally different roles that propositions are supposed to play. And the idea is, if we can sort of develop a theory of propositions, then we can have it play all of these roles. Now, in logic, in sort of a classical setting for Boolean logic, as Martin-Löf mentions, you could really, in a lot of cases, just talk about there being two propositions, the true one and the false one. And we don't care about what they are. Now, obviously, this doesn't work for analyzing meanings of sentences, right? Because snow is white is true, grass is green is true. They mean different things. So we can't say there is one thing they both mean, the true proposition. But, you know, we can sort of simplify in certain cases and sort of say, okay, we're actually just going to talk about true and false. But if you try to be more general than that, you can develop more sophisticated analyses of what propositions are. And there's lots of different things out there on the table. Some people will say that they're structured, usually structured sets of properties in individuals. So somehow it's a combination of whatever the property of being human is, for instance. Who knows what that is, right? But there's some abstract thing floating around out in the world somewhere that's the property of being human. And then there's me, the physical human. And if you put those two things together in some sort of ordered set, ordered pair, you get the proposition that Dustin Tucker is human. That's sort of the idea. Or you can talk about sets of possible worlds. So first you have to understand what a possible world is, and then you can say the set of all possible worlds where grass is green is what the proposition that grass is green means. And of course, that's different than the snow is white, because if you imagine all the possible worlds where grass is green, some of them will have non-white snow. And vice versa. You imagine all the worlds where snow is white, some of them will have non-green grass. And so that's how we can say those are different propositions. Obviously, then the problem becomes, okay, what is a possible world? And maybe also what's a set, right? Maybe you want to say, what are sets of things and what is a possible world? Or, okay, maybe we'll accept that we know what I am, but we don't know what the property of being human is, and we don't know what it is to have an ordered pair consisting of that property and me, the physical thing that I am, in there, right? Because we don't even know what ordered pairs are, let alone what ordered pairs containing physical objects, and we have lots and lots and lots of problems, right? But the idea is, you can sort of say, okay, this is what a proposition is. Now, why am I talking about this so much? Well, because the point that Martin-Löf is making, or one of the points that he's making, is that propositions are just these things, right? They are things that are true or false, but they're just like the thing itself, right? The thing that is meant, the thing that can be true or false. And then if we sit there assessing or judging that something is true or false, that a proposition is true or false, that action of judgment is about a proposition, but it's separate from the proposition, right? So we have multiple levels of multiple levels at which things are happening, right? We have the expression in English that we could use to express a proposition. Then we have the proposition itself. And then we have a judgment about the proposition saying that it is true or false. That's all before we talk about logic at all, right? That's just, here's some basic concepts of what we are judging and what we are making judgments about and so on. Okay. Now logic enters the picture. And the idea is logic is supposed to be a tool for helping us to express different pieces of information or relationships between information. So there should be some way of talking about propositions or referring to or meaning or denoting, expressing propositions. Okay, now we're going to take the really long detour, okay? So set everything about propositions aside for a second. Let's just talk about what it is to be a formal language or a language, okay? Because obviously we have natural languages, English, French, and so on, but we also have formal languages. And these are the languages that we see in logic, or we start studying in logic. One of the things that can be, I think, and I'm just guessing at this based on observation and a little bit of guesswork, but I really don't know much about this because I have not come up in my sort of intellectual development inside mathematics. But one thing I know about mathematics is that there's a real freedom using symbols all over the place, which makes sense. It's sort of one of the things that you learn very early on. We use plus and time symbols and things like that very early on when we're learning math, and we just sort of go from there. But then it's hard to separate the symbols from what they mean. And so the behavior of the symbol as just a syntactic, purely meaningless scribble on a page from its meaning. Now, Martin-Löf he says he's going to completely obliterate that distinction as well. He's going to be, as much as possible, trying to not distinguish between form, or the symbols, and their meaning. But I want to talk about what it looks like if you're really precise about that first. So I'm going to tell you about a language, and this language turns out to be equivalent to something you're probably familiar with, but I'm going to try to do it in a way that makes it at least feel a little bit foreign so we can see how we can think of it just as this purely abstract thing. Here's the language. The vocabulary of the language. The vocabulary of the language is every lowercase letter. That's not how you write a B. And they can also have subscripts if they want, if you need them. So 0, A1, so on, B0, B1, and so on. And so we just have all of the lowercase letters with any possible subscripts, numerical subscripts. We can go, okay? So our vocabulary is already infinite. We have infinitely many lowercase letters. We also have 2 capital letters. We have A and we have B. And that's it. That's my vocabulary, okay? Then I have a rule that says when some strings of vocabulary items count as good. So we can imagine strings of vocabulary items, right? Strings. And strings are just going to be a sequence of vocabulary items slammed together, right? So A, they have to be finite in length. A is a string, you know, B0, A, capital B, capital A, lowercase c is a string, and so on, right? And then we're going to say some strings are good. So which strings are good? We say any string consisting of exactly one lowercase letter is good.
This is like exactly one, like
instance of. Yep. So exactly one lowercase letter. Each letter. Don't think of the letter as like the type of thing. Each individual occurrence of the character. So one string, a one character string containing one lowercase letter, with or without a subscript, counts as good.
Okay.
So here are some good strings. And so on, right? Those are good strings. If phi, I'll use Greek letters as variables over strings. If phi is a good string, then so is the result of prepending A to it. So what are some other good strings? AA, AB, AC, AF0. Of course, we can do this again. So we can say AB is a good string, right?
Sorry, when you say good, are you referring to sort of like well-formedness?
Sure. I'm literally introducing the word good as just a meaningless technical term that's characterizing some of the strings.
We're not assigning any truth values here.
Nope.
This is just like a well-formed.
Yep, this is just a well-formedness thing. Yeah, think of this as well-formed, right? And then we can say if, and I'm being kind of verbose in all of this, and that's maybe irritating, but also intentional. I apologize, but we'll get there. If phi and psi are good, I'll be a little bit quicker, but you know, we'd write it out. Then so is the result of prepending B to their concatenation. So, well, if I were to say, take that as my phi and that as my psi, then I would concatenate them and get AC and then put a B in front of it, and that's a good or well-formed string. Basically, we have one place and a two-place operator, if you want to think about it like that. A is our one-place operator and B is a two-place operator. But again, I want us to sort of think of it in an abstract way because I want us to see that we can make this behave the way we want it to behave in the setting of logic, even though clearly nothing has any meaning here, right? Okay, so that's well-formed, or that's good. In particular, then something like this would be good. Right, so in that case, we have this as our phi and that as our psi. Right, so big B, big A, little a is a well-formed string, or it's a good string. Okay, those are the good strings. Now I'm going to tell you about some special strings. We're going to say, these are special. This. Okay, those are the 4 special strings. I hope the point of this, that this is hard to parse and just sort of a bunch of nonsense, might be getting across. Obviously I did not choose these at random, right? But these are special strings. And then I'm going to tell you how to get new special strings from old ones. Basically what I'm doing is I'm defining a way to get theorems and then get other theorems in a system of logic. But again, the point I want to make right now is that this is all meaningless stuff. And it's just going to sort of be clever selection of this meaningless stuff that's going to make the symbols behave in accordance with, or behave a lot like certain concepts. Okay. So, if phi is special and psi is good, then the result of uniformly substituting psi for every occurrence of a lowercase letter alpha in phi is also special. So, for instance, if I say phi is, let's just do, what am I going to care about? I'm going to care about this one. Let's look at our second one right now. Actually, yeah, whatever. B, A, B, A. We'll say psi is going to be A, and we'll say alpha is B. Then what this says is I can substitute my A in for every B in that formula and have another formula that counts as special. I said, if you have something that's special and you have a well-formed formula, basically something that's good, then you can plug in, uniformly substitute that well-formed formula for some lowercase letter and get something that is still good. Or sorry, to get something that is still special. For those of you wanting to keep track in your head, special means theorem. So, that is special, is a theorem. Here, let's do something more interesting. We're going to be working with this one, the fourth one there. I'll just make sure it's still on the screen. And we're going to say that's our phi, and then we're going to substitute, and we'll do multiple substitutions at once here just to save ourselves some space. But what we're going to do is we're going to plug in BAA for A. We're going to plug in A for B, and we're going to plug in big A little a for C. So those are the substitutions that I'm going to do. Actually, let's write it out like this so we can. Those are the substitutions that I'm going to do here. And actually, we can probably color code this even better. So let's do that. We'll do that. Okay. So if I take that initial string up there, I've got B, A, B, A, and then we have to put in B, A there, and then we have to put in A, we go back to B, A, B, we put in A, we put in B, A, we go back to this, B, we go A, and we go A. Okay, so what I did there was I started with this, and then I made the substitutions according to these three substitutions uniformly. Okay, I'm going to follow what happened there. Just on a purely syntactic moving symbols around level. And so the point I'm trying to make here is that there is absolutely nothing about meaning going on here at all, right? All I'm doing is giving you some rules for moving symbols around, and all I'm doing is calling certain results of those moving symbols around as good and special, right? Good means well-formed, special means theorem, but all I really said is, here are some things that I'm going to call good, and then using that classification as good, I'm going to then classify some subset of those, or some of the good things I'm going to classify as special. And I'm telling you how you can determine which things are special. There's one more way things have to be, you have to allow yourself to do to make things special, is if phi and psi are good, B A phi psi, let's see this, if those are good, and B A phi psi and phi are both special, then psi is special. Okay, why is that interesting? How can that be of any use to us? Well, if we take a look at what I just wrote down here, it has the following structure. It has that structure, right? And so it fits this structure overall, right? We've got the same BA here, and then we have a phi there, and then we have a psi there. And you can check and confirm that the two things, like this, these two things, those two strings are in fact good. So what this tells me, what this second rule I just wrote down here about being special tells me, is that if my phi is good or is special, then so is my psi, right? And it turns out this thing is special because this, right, capital B, capital A, capital B, and then 3 lowercase a's. Hey, that was the first special string that I said. That was the first string I called special. So what I've just found out is that thing's special. So I can write that down as a new special thing. I'm not going to do this for much longer. I'm going to follow how I said, okay, this gets to be special now. Okay, cool. Finally, we have that. But we're not going to want to break it down like that because we're also going to want to break it down. Actually, hold on. Let me just see if I can. Okay, here's one more thing we're going to do. I mentioned already that was special. Right? That was the other special thing that I mentioned. That was the first one where I could do this substitution thing. I said, okay, this is special, right? Okay, well, turns out that is sitting right here. All right, let's color code this the same way. So we just got another thing here that has this same structure. And that is the same as that. So a second application of this whole rule that we just talked about here tells me that just this formula, or that string, is special. Cool. So another thing that's special now is this. Okay. My point here was I made up these rules about being special and being good. I told you here are 4 specific things that get counted as special, and here are 2 ways to get new special things from old things. Okay? New special things from old special things. And then, with a couple applications, we were able to find out that this was special. And this actually is a pretty interesting thing to be special. Because what I've just done here is I've defined, B and A, these 2-place and 1-place operators, and basically, and what the 4 starting special things, which are axioms, and the 2 rules that I said for getting new things from old things, which are, you could call them rules of inference or transformation rules or whatever. This is what I've just given you is a satisfactory axiomatization of Boolean logic, of the logic of ands and ors and nots. And I did it because what this is, using Polish notation, basically is whenever you have A phi, that's just phi is false, and when you have B phi psi, that's just phi or psi. So, for instance, what we have here is not A or A. Or A implies A, using material implication as defined by an or with a negation on it. Okay, the reason I went through all of this to point this out is that I want to drive home the fact that all we have are dumb rules that have no concept of meaning whatsoever, moving symbols around. And it's just sort of, if you cleverly select your starting point, I'd be clear, I did not cleverly select any of this. This is all lifted from Principia Mathematica over 100 years ago. But if you cleverly select your starting points and you cleverly select your rules, so you cleverly select your axioms and your transformation rules, you get something that behaves just the way we'd want. But the crucial thing that I want to point out here is it's just like behavior that is imposed by the rules we've created. So now, let's talk about propositions and meaning again. I should also keep track of the time. So, let's actually go back here. I have no idea what that was. B-A-A-A, okay. So, let's just put down a couple of things that we said were special, right? B-A-A-A, or, I don't know, I'm just going to copy this one, because I want it, but I don't want to have to use it again. Oops, that's not what I want to do. I have to say that once I started using a computer for things like this, I really got kind of spoiled by it. It's awfully nice. Okay, so those were a couple special things. And if you want to break this one down, it ends up meaning this. If A implies B, then C or A implies C or B. But what I want to do right now is talk about, like, all I did was give you purely syntactic rules for moving things around. There was absolutely no meaning there. So when Martin-Löf talks about inductive definition of this is on page 2 again. Ultimately, what I'm doing is trying to work through page 2 here. Here, you know what I can do? I can even just pull this up. Let's do that. We'll go here. We'll go here. And we'll do this. That did not do what I wanted to do. Stop it. We'll do this. We'll do that. We'll do that. We'll do this. Okay, so this is from the Martin-Löf notes, right? And again, I just did Boolean logic here, so I didn't have to talk about terms. Terms are what you get when you start talking about first-order logic. But we had the inductive definition of formulas, right? And we had the specification of axioms and rules of inference. And that's what we've got. And so far, all that's done is said, these are some strings that I get to count as good, or theorems. Or, I'm sorry, special. Good, I'm forgetting my own made-up terminology. Special, right? They're theorems. So you can think of the strings of symbols as corresponding to sentences in a language that can refer to propositions. And then saying certain of them are special strings is saying that those denote true propositions. And that's the idea of going to this third step of the semantical interpretation. So what we then want to do is say, okay, strings or sorry, not strings, good strings are like sentences. They denote propositions. And then special strings are like true sentences. They denote true propositions. Whenever we're talking about denoting something, what we're doing is we are talking specifically about interpreting the language, assigning meaning to the things in our language. Now, what are propositions? Well, this is where, as he says, if you're dealing just with Boolean logic, propositional logic, you don't actually need propositions to be anything more than the true and the false. You just need two of them. The true one and the false one. Because you don't care about anything else. If I'm doing just my propositional logic, all I care about is little a true or false? Is big A little a true or false? Right? That's all I need to be able to calculate all the meaning that exists as far as I'm concerned for doing what I'm usually doing with propositional logic. So instead of saying they denote propositions, we can just say they denote either a 0 or a 1, or a T or an F, or whatever. And then, notably, we don't even have to say, like, one thing we could do is say they just denote, let's say, M and N, okay? Those are going to be the two things they denote. I don't care. Just the capital letter M is one proposition, the capital letter N is the other one. Now, the point is, again, even in my semantical interpretation, all I've done is interpreted things by saying they refer to one of two letters, right? And that still doesn't mean I know which one's supposed to be true. And in fact, depending on how I assigned my rules, all I said was I've got one unary operator and one binary operator, right? So the binary operator, as far as I know from the sort of rules that I assigned for, or telling when you can be an M and when you can be an N, I have to tell it how it behaves before I make it behave like OR, right? Basically, I say, B, phi, psi gets to be in group M as long as at least one of the other two things is in group M, and then that makes it behave like OR as long as I'm saying M behaves like true. But it would make it behave like AND if I said M behaves like false, right? Again, the point here is that there's sort of no meaning to these things except what we have forced on them, the way we're making them behave. And then the special strings, the theorems, and I'm going to keep saying denote, they denote true propositions, right? They're the special ones. So we're talking about denotation here. We don't want to say that the special string is true. It's true. It just denotes something that counts as the true proposition or whatever. Okay. So then, where does the notion of a judgment come in? Well, a judgment is saying this string is special, right? Because saying this string is special, given the semantical interpretation, amounts to saying this string is true. Which, again, means this string denotes a true proposition, because the idea is the propositions are really the bearers of truth, right? M and N are the things that get to be true or false, and we just say, okay, M is going to be the true one, then N is going to be the false one, or whatever. Okay. So, and maybe I should write this down, because this is sort of the thing I was trying to build to, right? Again, the thing that we need to point out here is that this judgment on its own still doesn't have any meaning, because what he's saying is that the judgment, what he actually says is A is true is the judgment, right? So really, what we have to do is break this phi a special thing down into something more like this. Phi denotes a true proposition. He moves really swiftly between a couple of different things, and I want to point out that this is something that we can say. Here, let's clean this up a little bit. I want to point out that the thing I mentioned here about special, this and this don't mean the same thing, right? And hopefully that has become clear at this point. Phi is special is just syntactic, according to syntactic rules of inference. Phi denotes a true proposition only enters the picture once we've added the semantical interpretation for our arbitrary lists of symbols in our string. So basically, this is all that's needed to say phi is special. But this is required to get us down to this. Right? I'll make it a little smaller. Right? So we need the inductive definition in terms of formulas, and we need the specification of axioms and rules of inference to say that phi is special. But to make the extra step, we have to add in the semantical interpretation. Okay. If you go study most things in logic, you will, and as he says, if you in a standard textbook presentation of first-order logic, but really, if you study lots of things in logic, you will find it presented like this. Right? You will find it presented where you've got this purely syntactic characterization of some strings of symbols, and then you've got something else modeling the behavior of those strings of symbols, and then you've got your rules of inference, and the hope is that your rules of inference perfectly correspond to the model. And of course, well, maybe not of course, but, and then, and actually, maybe that's something I should mention here briefly, because he does throw this in as an aside, and I want to sort of draw attention to it. This is determined, phi being special is determined purely by the stuff highlighted in yellow. But this is being determined purely by the semantical interpretation. There's no overlap there. There's no crosstalk there. So the semantical interpretation is something that we do independent of the axioms and saying that things are theorems or special or whatever. So the reason that's important is because then there's a separate question of, do my rules perfectly correspond to my assignment of meanings, right? And this is where Gödel comes in and incompleteness comes in. Incompleteness says that if you're trying to create a semantical interpretation for a language that's rich enough to capture some basic stuff about arithmetic, multiplication and addition of natural numbers, you're never going to have a perfect set of rules. You'll always have some disconnect between the stuff in yellow and the stuff in blue. But anyway, that's sort of the sort of thing we can build off of there. But this is the backdrop that he's working against. So when he says things like, we will avoid keeping form and meaning apart, right? What he's saying is, we are going to start talking about these symbols and using these symbols while also talking about their meanings. So, where he says something that I want to clarify a little bit. He says this rule by itself is taking for granted that A and B are formulas, and taking for granted, and then saying, or sorry, it's taking for granted that A and B are formulas, and then it's saying that we can infer that A or B is true, A or B is true, given that we know that A is true, right? Well, even that is already throwing in this talk of truth. And again, strictly speaking, even you're not even going to find that. Right? Strictly speaking, all you're going to see is something like this. If phi and psi, I'm just using phi and psi to be consistent with what I was saying before. If phi and psi are good, and phi is special, then B phi psi is special. Right? And that's another way of saying this, and it's making explicit what he said is still left implicit. And it's true. A lot of the time you'll see that left implicit. But this is a way of making it explicit. But what he writes is this. Or using the same notation that he's writing, he would write it like this. So I just want to point out again that this is when he talks about like ignoring the distinction between form and meaning and like working with semantical interpretations right off the bat, this is how sort of it's all being packed into one place. And again, do you need to understand this to be able to understand the rest of his notes? Probably not, but hopefully this clarifies what's going on these pages. I'm gonna end here. I'm gonna stop after this basically. So I up here was saying phi and psi are good. That was a purely syntactic property of the strings of symbols. We're already past that here because we're saying not just they're good, they refer to or denote a proposition, or they are a proposition. If we're going to be this, we don't have to say they denote a proposition. At this point, we're going to say phi is a proposition, right? Something like that. And then again, I said phi is special, but down here, he's saying phi is true. Again, that's introducing this extra step already of semantically of an interpretation where talk about truth even makes sense. Talk about propositions and truth even makes sense. And then, of course, the conclusion here, saying that's special, he goes to saying it's true as well there. Okay. I'll stop there because I got started really late and it is already 4:51.